Good afternoon, everyone. How are you? So today is the second lecture of EMI. In the first lecture, what we did, we studied about magnetic flux, like what is magnetic flux and what is its similarity with the electric flux. Solved some questions about magnetic flux. When it is zero, when it is maximum, we have seen those situations. I hope you can recall it from the previous classes. Now, after that, what we did, we studied about Faraday's experiment, the laws of Faraday, the conclusions of the Faraday's experiments, and the most important thing was Lenz law. What was Lenz law? I will recall you in with few examples as well after this conversation. The Lenz law was the statement which is basically a conservation of energy statement. Lenz law was, this is a very simple question and asked many times, like on which conservation principle Lenz law works? It works on conservation of energy. You should remember this thing all the time. Now, moving further, I have given you a homework question based on Lenz law. So I will try to describe and you will try to understand how it works. Okay, so this is your homework question. I will check whether you have completed or not. Okay, so I will just describe the question first and then straight away I will go with the solution. Okay. If you can see, there is a long wire. You can see there is a long wire which has some current I. If I can use some laser pointer, this is a long wire and it has some current I, and this current is not constant. Actually, this current is increasing with the time. And on the same page or on the same paper, there is a circular loop placed. The loop is in the XY plane, and the wire is in the Y axis. Clear? So what question says, find the direction of the induced current in the loop. They are asking you the direction of induced current. So if you don't know the Lenz law or the steps to follow, I will just describe it in steps. What was that? First of all, what should be your first step to find the direction of induced current? Your first step should be identify the direction of original magnetic field. Your first step should be identify original magnetic field. So I am writing it here, identify check the spelling of original, I will say magnetic field. Let's suppose original magnetic field I will denote with B naught. So if you look into this diagram, who is creating the magnetic field? This long wire is creating the magnetic field. And what is my point of interest or what is my location of interest is the loop. So in this plane or in this area of the loop, what will be the direction of the magnetic field? You can use your right hand and you will get the direction into the plane. So B original is into the plane. I hope this is clear. Now, first step is done. Second step says, look for change in flux, whether flux is changing or not, because change in flux is the only cause of induced EMF. So what you can do, look for change in flux. If flux is changing or not. If flux is not changing, flux is constant, then you can say no current will be induced. If flux is increasing, then current will be something like that. It will try to oppose the increase in flux, and vice versa is also true. So can you see that as this current is increasing, can you see that magnetic field will also increase? This magnetic field will increase. And if this magnetic field is increased, the flux will also increase. That means current will induce. Now task is to, I will say in the next step, what you should do, identify or try to oppose this original field, or try to oppose the change in the magnetic field, or try to oppose the change which is producing induced current. That means increase flux is increasing. So your task is to decrease the flux. What you can do, just induce some other magnetic field which is opposite to that, because you want to decrease the flux. So how you can decrease the flux? If there is another magnetic field, so another magnetic field, what should be the third step? Identify the direction of new magnetic field. New magnetic field, or you can say induced magnetic field. Actually, magnetic field is not induced, current is going to be induced, and that current will create some magnetic field. So I am saying new magnetic field. So what should be its direction? Its direction should be something like that, which opposes the change in flux. So original field is inside, which is increasing, or flux is increasing. So new field or induced field should be opposite to that. That means outward. Now, what should be your step 4? Use right hand thumb rule. Thumb rule to find direction of current. Is it clear? Now, how you can use your right hand to find the direction of current? Simply put the thumb of your right hand in the direction of new magnetic field, which I have denoted by BI. Now, my thumb is outside the plane, coming towards me outside, and close the fist. The direction in which your fingers are curling is the direction of the induced current. So you can see that induced current will be something like that. This is anti-clockwise. This is anti-clockwise. So you can mark your answer as anti-clockwise. Now you can do these things very quickly. I will give you some time. After one more question, I will give you one more question. So is this clear to everyone? Moving further. Okay. Now we have some recall questions based on this Lange law concept. So you can do it. Look at the question. You have some 30 seconds to answer the question. Their question says the direction of induced current in loop 1 and 2 will be respectively. This is loop 1, this is loop 2, and the thing which is given also, which is also given in the question, is that the current is I and this current is decreasing. This is the part of the question. This current is decreasing according to the question. Now you can solve this question. You have 30 seconds to answer. Okay. Look. First of all, if I say locate original field, and if you look at the diagram, what will be the original field using right hand thumb rule? Who is creating the field? The long wire is creating the field, and you can use your right hand. Then in this loop 1 region, original field is outward, and in this region, original field is inward. This is original field. Now again, current is decreasing. That means flux will be decreasing. Your task is to support it. Support it means you need to support the magnetic field. So new magnetic field, if I change the color of the pen, new magnetic field should also be in the same direction to support it. or new magnetic field should also be in the direction to support it. That means into the plane, and here it is outward to the plane. Now just put your right hand and thumb in the direction of induced field. And if you do that, you will find that current in this first loop will be in this direction. What is this direction? Anti-clockwise. And in this, will be clockwise. So in the first loop, it is anti-clockwise. In the second loop, it is clockwise. So option B is correct. I hope it is clear to everyone. Is there any doubt? Okay. So on this note, I am giving you one more question. The question is on your screen. Now this time, you can see that current is constant. You can see that current is constant. Now answer the question. You have another 30 seconds, or I will say some 30-40 seconds to answer the question. Look carefully. The wire is long, as you can see from the diagram. Okay. The first thing is, first of all, we will identify the field. So original field, can anyone tell me where will be the original field? I hope most of you can answer this. This is basic thing. Where should be the original field? Yes. Original field is into the plane. Very good. Now, is this field changing? Or what happened if I look for the first loop? Look at the first loop. The first loop is moving in the upward direction. It is at the same perpendicular distance from the wire. It will remain at the same perpendicular distance from the wire because it is moving vertically upward or parallel to the wire. Can you see that? So if it is at the same perpendicular distance from the wire, that means flux will remain same. Why flux will remain same? Because field will remain same and flux will also remain same. Now look at the second loop. If I look at the second loop, what will happen? It is moving away from the wire. That means the distance of wire and loop increasing. And this distance is increasing. That means magnetic field is decreasing and flux will also decrease. So flux will decreasing right now in this case. Flux is decreasing. Are you getting my point? Can you see that without taking so much stress on your mind? Can you identify this thing? If flux is decreasing, your task is to support the magnetic field. Where is the original magnetic field? You can say original magnetic field was, sir, into the plane. So new magnetic field should be into the plane to support the original field. And if you can see that to support the original field, if I put my right hand into the plane and curl my fingers, the current will be in the clockwise direction, something like that. This is going to be the current. So in the second loop, it is clockwise, clockwise. And in the first loop, there will be no current. That means 0 and clockwise will be my answer, which is correct option number C. I hope this is clear to everyone. Each and everyone can answer these questions. Right. Very good. Moving further with some new topics. So what you can say, the Lange law, how it can be used. Now you know that on which principle it works. It works on the principle of conservation of energy. I hope these two things are very much clear to you. Moving further. Now there comes a point, motional EMF. This is again very important topic, or I can easily write important in front of it. Important. If you see the previous year questions, out of 10 questions, 6 or 7 are basically from motional EMF. So you can just get an idea what is the importance of motional EMF and how much variation is available in that. Okay. Now listen to me very carefully. Let's suppose, what you can suppose, suppose there is a rod, conducting rod, obviously, I'm talking about. There is a conducting rod. Let's suppose the length of the rod is L. Clear? And there is a uniform magnetic field B all over the place. And this magnetic field is into the plane. This magnetic field is into the plane. Let's suppose its magnitude is B. And this rod is moving with certain velocity V. This rod is moving with certain velocity V. Now, in this diagram, if I clearly specify, velocity is in the x direction, or I can mention it here. This velocity is in the x direction. Magnetic field is in the z direction. I'm talking about the diagram only, nothing else. This length is along y axis. Clear? Now, after some calculations, I will get some EMF. So one thing that you should understand, when a conductor moves in a magnetic field, a potential difference is created across its ends. How this potential difference is created, it depends, or it is based on the principle of force on a moving charge. The electrons inside its conductor has some electrons, like these electrons. These electrons will experience forces and they gets collected at the bottom. At the bottom, like this. They gets collected at the bottom and it become negatively charged. Similarly, some positive charge is created at the topmost point due to its motion. So it creates some potential difference, positive and negative, and potential difference is created. This potential difference we call as EMF. So how much EMF is created? You should remember only that thing. That EMF that is created is P L V. Now, formula is very simple. It might look like the easiest one, but you should be very careful while using this relation. What are the limitations and what are the conclusions that you should follow? And what are the punchlines you need to remember? I will tell you. Look at the punchlines. Punchlines. So what is the first punchline that you should keep in mind? BLV. All these three terms must be perpendicular to each other. I'm saying it and you should follow it. What is first line? B, L, and V should be mutually perpendicular. . 。 . 。 . 。 . Now, someone might say, sir, if it is not perpendicular, like if velocity is not perpendicular to the length, then you should take the component of velocity which is perpendicular to the length. You cannot use it directly. You need to take the component which is perpendicular to the length. Are you getting my point? So first thing that you should keep in mind, B, L and V should be mutually perpendicular. If it is not so, like if not, they are not perpendicular, or if any two are parallel, you can identify this is written as parallel. If any two are parallel or anti-parallel, like angle 0 or 180 degree, parallel or anti-parallel, you can directly use it. Any two are parallel, then induced EMF will be 0. Mark my words. This is the very important punchline. Is it clear? Okay. Second punchline is, I will give you some example. Like, just take an example before I write the second statement. I will write the second punchline on the next slide. So just take an example. Let's suppose this is a rod of length L. Magnetic field is in the upward direction B, and velocity is in the horizontal direction like this. So what will be the EMF induced? Someone is asking you what will be the EMF induced. So you can clearly see that two quantities are parallel to each other. Which are the two quantities? You can see length is parallel to the magnetic field. Can you see this? Here, length is parallel to the magnetic field. Can you see that? And if any two are parallel, then you can directly say EMF is going to be 0. Just make it in your mind, establish in your mind. I will give you some questions to remember that, so that you can remember the things moving further on the next slide. Is it clear till now? The relation motional EMF BLV, where all these three must be perpendicular to each other. If it is not so, then you can take a component of that which is perpendicular. Another thing, if any two of them are parallel to each other, then EMF will be 0. Now, there are some questions on the next screen. Okay. You need to answer for the first question. Just answer for the first question. Find EMF induced in each case. So I am talking about first. So in the first case, if I talk about, can anyone see what will be the answer? Can you see one thing which is very much clear, which is very much evident from this, that velocity is parallel to the magnetic field? Yes, we can see that. If velocity is parallel to the magnetic field, you can conclude that EMF will be 0. Clear? Now in the second question, if I talk, magnetic field is into the plane, length is along y-axis, but velocity is also along y-axis. Here, length is parallel to the velocity. That means EMF will again be 0. How simple is that? You can identify. You need to identify it very quickly. Now on the next slide. Here. Is there any quantity which is parallel to each other? Like magnetic field is into the z-axis, into the plane. Length is somewhat in xy plane. Velocity is somewhere. So nothing is parallel. That means EMF is not going to be 0. Now what you should do? EMF is equals to B, L. Can you see that B and L both are perpendicular to each other? This length is L. They are perpendicular to each other. You can see that magnetic field is into the z-axis and rod is somewhere in the xy plane. They are perpendicular. Now, what you can do, take the component which is perpendicular to the length. take the component of this velocity which is perpendicular to the length. So can you see that this component will be v cos theta and this component will be v sin theta. Can you see that? So which component of velocity we will use? The component which is perpendicular to the length. So which component is perpendicular is v cos theta. That is VLV cos theta. I am again saying this is not the standard result to remember. What is the standard thing? Sometimes you may find that VLV sin theta is written in most of the books. So it's not a standard result that BLV cos theta is the standard or BLV sin theta is the standard. It depends on the angle from which it is given. The angle, it depends on the angle. So right now, what if I say, in the next question, which is again very important to you, you can see the question says, find EMF in each case. In this question, the wire or the rod is not straight. It has some irregular shape. So now coming back to the second punchline, if I can say, what is the second punchline? The EMF induced, the formula of EMF induced that we have studied in the previous slide here. Here L is what? The L is what? Effective length. L is what? Effective length. What is the meaning of this effective length? Effective length is something like, you can say, from starting point to the end point, the line joining the initial point to the final point is the effective length. So coming back to the question, if I say, here you can see, this is the point A, which is the starting point. This is point B, which is last point. So this is the effective length. This is the effective length. And in the question, something else is given. What it is given? The angle of the velocity with the vertical is given as theta. This angle is given as theta in the question. Now, if I change the color of the pen and if I start writing with the yellow color again, you can transform this ACB wire like this one. This is AB wire. And the velocity is something this one at an angle theta. This is the velocity. So you can simply transform the irregular shaped wire with the L effective. Now, if I say, what will be the two components of the velocity? You can see magnetic field is into the plane, which is perpendicular to the length. Now you can take the component. This component is going to be V sin theta. And this component will be V cos theta. Clear? Now, which component you will take while writing the EMF? So EMF will be V, L, and which component you will take? The perpendicular component, which is V sin theta. Is it clear? Is it clear to everyone? I hope this question is also clear. Can we move further? Okay. So I am giving you one question in the homework. I am giving you one question in the homework. So this is going to be your homework question. This is going to be your homework question. Like this. Like homework question. There is a rod two rods are connected such that this is AOB and it makes an angle theta. Clear? And this length is L, this length is also L. Done. And this complete system is moving with some velocity V. And there is a magnetic field B. Tell me the EMF induced in the system, or the total EMF induced in the system of rods. There are two rods, AO and OB, both of length L. They are connected to each other at a certain angle theta, and the system is moving towards right with a velocity V. Clear? You need to answer the EMF induced. Done. I hope question is clear to everyone. Find EMF induced in the system. Done. Now, there is one question which is left behind that you should ask actually. Whenever I am saying that EMF is induced, whenever I am saying that some kind of EMF is induced, then it can be represented by a cell like this one. It can be represented by a cell. And you remember that there is a positive terminal and there is a negative terminal in the cell. So how can we identify which side of the rod is going to be a positive terminal and which side is going to be a negative terminal? So to understand that, I'm taking you backward towards the main slide, and how to do that, like here. You can use right hand Fleming rule to identify the positive and negative terminals. What you can use the Fleming rule. How you can use the Fleming rule? First of all, take your right hand. Take your right hand. I will give you another way as well. Second thing, make all three fingers, the thumb, first finger and second finger, perpendicular to each other like this. All three should be perpendicular to each other. Now, second thing, put the first finger in the direction of magnetic field. I'm saying Fleming right hand rule. What are the three things? Thumb, first finger, second finger. Make them perpendicular to each other. And what you should do, put the first finger, this is your first finger in the direction of magnetic field, that is B. Clear? Thumb in the direction of motion. Thumb in the direction of motion. Then second finger will give you the direction of positive terminal. Positive end, or you can say high potential. It will give you the high potential. Like here you can see, if I use the right hand thumb rule or right hand Fleming rule, the thumb should be in the direction of motion, first finger in the direction of magnetic field. If my magnetic field is into the plane, I am putting my first finger in the direction of magnetic field. My thumb is in the direction of motion. So my second finger is giving me the direction of positive terminal, which is upward. That means my positive terminal is going to be in the upward direction. Is it clear to everyone? Okay. That means the positive end I have mentioned here, this is our positive end, this is our obviously the negative end. So how it can be represented? This can be represented like this one. With EMF E and resistance R. Sir, what is this R? This R is the resistance of the wire, resistance of the rod. which behaves as the internal resistance, which behaves as the internal resistance. I hope this is clear. Now we know the directions, we know the magnitude, we know the punch lines, everything we know about motional EMF. So it's time to move ahead. Now, the next topic is EMF induced due to the rotation. This is again an important topic. Before starting the topic, you can drink some water. I'm also drinking some water. Okay. This is again a thing to remember, useful for the NEET exam, for the mains exam, and for every exam in your boards too. Okay. Let's suppose what, let's assume there is a rod. Very good. There is a rod of length L. Clear? And this rod is hinged at one of its ends. Are you getting my point? This rod is hinged at one of its point like this. This is the rod and it is hinged at this point. And hinged means it can be moved freely in this plane of the paper. So this rod is now rotated with some velocity. Rotated with some velocity, and let's suppose there is a magnetic field B going into the plane of the paper. Clear? And this rod is given some velocity omega. Clear? So this rod will move almost in a circular path, if I say. I am not sure about the uh, my drawing skills, but it will move something like that. Clear? Yes, sir. The diagram is quite good. Yes, looking good. So it will move in a circular path. Then what is our task is to find the EMF induced in the rod. Clear? Now, for that, you can see, we know that EMF induced is BLP. We have studied this formula only. Now, in this scene or in this situation, you can see that if you focus this part of the rod, I'm taking a very small part. If you take a small part of this element, the velocity of this part will be something different as compared to the part which is at the end of the rod. Are you getting my point? Why this velocity is different? Why this velocity is different? Because the distance from the center is more, or from the axis is more. I hope you know the distance formula, na? V is equals to what? V is equals to R omega. I hope everybody remembers. So as you move away from the center, the velocity will increase. That means velocity throughout the rod is not constant, and whenever a quantity in a relation is not constant, we can use integration to solve the answer, to get the answer. Now, are you getting my point? Why I am coming towards integration, and how you can feel that integration is going to happen. I hope this is clear. Now, I hope I can delete this. Okay, I can't. Let it be. Otherwise, the whole rod will be deleted. I think so. No problem. Now, coming back to the question. So, for integration, what I choose a small element of length dx at a distance x. Clear? So, I will write the EMF for this small element. Then I will integrate it for the whole rod. Clear? Okay. Now again, what I write, EMF induced in small element. You can write it as BE is equals to magnetic field is B. What is the length of this small element? You are talking about a small element which has a length dx. So what is the length? Dx. Very good. Most of you might made a mistake. You might have written that x is the length. No, x is not the length. We are talking about this small element which is of length dx only. What is the velocity of this small element? If you take this point, and what will be the velocity? V is equals to r omega, you know that. And what is the distance? What is the radius of this point is, you can say x. So velocity is what? X omega. Is it clear? This is a small, I will say, EMF induced in the small element. Now, for complete rod, what you can do? You can do the integration of Bx omega dx. I have written it here. Now take the integration. What will be the limit? Limit is 0 to L. Now if you integrate it, E is equals to B and omega is constant. What will remain? X dx. Integration of x dx is nothing but x square by 2. Limit is 0 to L. So induced EMF will be half B omega L square. This is the very much standard result for a rod rotating in uniform magnetic field B. Half B omega L square. Half B omega L square. Is it clear? Now there is one variation as well. What will be that variation? The examiner may ask you, what if, or you can say special case, if rod is hinged at the midpoint. If rod is hinged at the midpoint, then how it will look like? You can feel it that this is the rod. It is hinged at the midpoint. Now it is given some velocity omega. Now what will be its path? What will be its path? Or what will be its radius? Can you see? If it is hinged at the midpoint, like you can see in my hand, it is hinged at the midpoint and it is rotated. So it will rotate something like that. Can you see that? So is its radius is L by 2 now. So it will move in a circular path, something like that. I don't think it's good drawing, but you can assume that it will revolve in a circular path like that. So while solving, everything will remain same, but when you put the limits, so EMF will become minus L by 2 to L by 2. This is minus L by 2, this is plus L by 2, and everything will remain same. And if you put the limits, you will get EMF as 0. So what is the conclusion? If you hinge the rod at the midpoint and rotate it in a circular path, then the EMF induced will be zero. And if you hinged it at the end of the rod, the EMF induced will be half B omega L square. Is it clear? I hope it is. Can you remember this formula? Direct questions are asked from this. Direct questions without any change. Last year in 2023, question was asked in any one of the shifts or more than one of the shifts. So there is a checkpoint. Okay. So I will give you some 40 seconds to solve this one. चलिए करें start. Anyone? Anyone got the answer? 40 seconds done. Now it's time to start the question. There is a rod PQ of length 2L. Mark the keywords length 2L is rotating about 1 and P. That means it is rotating about end P. So first of all, draw the rod. This is the rod PQ. Clear? PQ. And the length is 2L. Clear? Length is 2L. The thing that we have studied, I have drawn it. In a uniform magnetic field B, which is perpendicular to the plane of rotation. That means there is a magnetic field B, which is perpendicular to the. Okay. Point M is the midpoint of the rod. Okay, let's draw a midpoint as well. Point M is the midpoint of the rod. Find the induced EMF between M and Q. Okay, so they are asking M and Q. Okay, if that between P and Q is 100 volt. Okay, so they are saying EMF induced between P and Q is 100 volt. No problem. And I have to find for M and Q. Okay, so as you study the question, as you read the question, the common mistake that you definitely did or that you will definitely do is you will not read the question carefully and you will forget. As you see, the point M is the midpoint of the rod. Suddenly the thing came to your mind that if it is hinged at the midpoint, then EMF induced will be zero. And this thing will ruin everything and your mind will stuck at this point only. But again, come back to the question. The rod is hinged rotating about 1 end P. That means it is rotating about the end only. M is just a point on the rod. It is not mentioned that rod is rotating about M. Are you getting my point? Some things you need to be very much alert while reading the question. Okay, so rod is rotating about point P and that you should keep in mind. Now, there are various ways to solve the question, out of which I am doing it very simple way. EMF induced in the PQ part, I will say. What will be the EMF induced in the PQ part? That is half B omega and length square. Length is what? 2L. That means 4L square. And this value is given as 100. This value is given as 100 volt. Let it be question number 1. Now, if I assume, that what is the potential difference between P and M? What will be the potential difference between P and M? I can assume that rod is of length L only. Can you see that? If rod was of only length L, then it will be look something like that. So I'm saying EMF induced for the part P and M will be half B omega, and what will be the length of this portion is L. Clear? Now you can see from the first equation half B omega L square. Can you cancel things out? 4 can be cancelled out by 25. That means half B omega L square is just 25. So EMF between P and M is what? 25 volt. P and M has a EMF 25 volt. P and Q has a total 100 volt potential. So this M and Q will have a potential of 75 volt, and that will be your answer. That will be your answer. Question is done. Understood? What's happening, sir? What you did? I did nothing special. You want to find the EMF of M and Q. There are various ways. There are various ways to solve this part. But what I did, I solved it for EMF for P and Q. Like I have assumed that whole rod is rotated, and if half of the rod is rotated, EMF will be half B omega L square. So I got the value of half B omega L square from the first equation. Put it here, and what you will get, this is 25 volt, total is 100 volt, so this should be 75 volt. Done. Next question. And this question is going to be your homework. So you got 2 homeworks in this class. I hope you will do the homework because time is up for the next class. So let's end the session. Okay. Bye everyone.